All right, let's get on track. So last time, we talked about induction and saw many examples of proofs by induction. So today, we're going to talk about something closely related to induction, which is recursion. So what is recursion? Let me try to keep my handwriting neat. Recursion is when, so let me give kind of a vague definition first, and then I'll say some more precise things and we'll see lots of examples. So, but recursion is essentially when something refers to itself. So the most common examples that you might see are defining a sequence in terms of what came before in the sequence. Or another common example is defining a procedure or a program in which there's a step in this procedure or in this program to start the procedure again on some other, usually smaller example. Another input, let's say. So we will see examples of all these things in due time. But let's start with the first one, because that's sort of the easiest place to start. So define a sequence of numbers, A0, A1, A2, and so on, by the following rules. So A0 we declare is equal to 1, and AN, for n greater than 1, is defined to be 2 times AN minus 1. So first of all, you can see how this is very much related to induction. This is essentially writing down some base case where we do it in sort of the first case to get started. And then we have some, recursive step or inductive step where we go from something previously in the sequence to find the next thing in the sequence. So for example, how would we compute the terms of the sequence? Well, A0 is 1, A2 is 2 times the previous term. So it is 2. A3 is 2 times this previous term, so now it's 4. A4 is 2 times this previous term, which is 8, and so on. So this is an example of a recursively defined sequence. And in this case, we can actually give quite easily a closed form. So a closed form essentially means a non-recursive formula for the terms. So in this case, we can give a formula for A sub n, is just 2 to the n minus 1. No, 2 to the n, yeah, because 2 to the 0 is 1. I'm afraid that I have misnumbered my sequence a little bit. So I started with a 0. So the next one should be a1, a2, and a3, and so on. Okay, and now this formula checks out because a to the 1, or 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, etc., etc. So we have this non-recursive form, which can be quite a nice way of working with things. But there are cases when recursive forms are easier to work with. So we may sometimes do that as well. So here's a famous example. Which is the Fibonacci numbers, which we will call F0, F1, F2, and so on. And these are defined by a recurrence relation. So F0 is defined to be 0, and F1 is defined to be 1. Now you can see, just like for induction, we don't always have to limit ourselves to one previous term and one base case. We can have situations where we have, for example, in this case, 2 base cases, and Fn will depend on the 2 previous terms, and it is just their sum. So this is more like strong induction, which we talked about last time. So let's compute some terms in this sequence. So F0 is 0, F1 is 1, then F2 is 0 plus 1, which is 1. F3 is 1 plus 1, which is 2. F4 is 1 plus 2, which is 3. And then F5 is 2 plus 3, which is 5. F6 is 5 plus 3, which is 8, and so on. And, well, here is already an example where finding a closed form is much more involved. And there is a way to do it, but I will leave that to an extra topic on Piazza, because it is outside the scope of the textbook, at least. So we're going to leave that for an extra.